Our next, for the last one for today is Skip Crilly. Since 2014, Skip has been a volunteer science ambassador at the Green Bank Observatory. His job includes maintaining and improving the performance of the 40-foot educational telescope at Green Bank. Prior to this work, Skip was Chief Technology Officer at 2 wireless equipment companies. Prior to that, Skip worked 27 years at Hewlett-Packard Company developing test equipment for the communications industry. Skip has built and observed with numerous radio telescopes and interferometers. He built his first radio telescope while a teenager in Manila, Philippines, where he grew up. Skip's current interest is the search for extraterrestrial intelligence using radio. Okay, go ahead, Skip.
Okay, good. Can everybody hear me?
Yes.
Good, okay, great. You can see my screen?
Yes.
Screen's up. Okay, good. Super, yeah, thank you, Rich. Thank you for the introduction. I'm going to give a presentation about SETI. I've been doing SETI for a very, very long time. Very interested in it. And something really fun happened a couple of years ago at a SARA conference when Rich Russell and I were talking about, wow, maybe we could do 2 antennas, the 60-foot Deep Space Exploration Society Plishner dish in Colorado and the 40-foot dish in Green Bank, where I work. And I had been going to Green Bank for about, 3 years when I started bringing my computer from home and looking for strange pulses on the 40-foot telescope while I was there part-time, maintaining the telescope. So we set up a system which is quite, I think, it might be fairly unique. I haven't talked to people who've done anything quite like this. The idea is that radio frequency interference is such a headache that doing single dish SETI is a really difficult problem. I've tried it for a long time and I concluded that you really have to have multiple separated antennas and look simultaneously. So in 2017, we started setting up a system. One is at Haswell, Colorado on the 60-foot dish, the 40-foot dish in West Virginia, and then starting late last year, we added in a telescope that's on my farm that I built. It's a 26-foot dish. The idea is just to put computers on all 3 and run them autonomously, running FFTs, and they capture 1395 to 1455 megahertz in 3.7 hertz channels. And I have other presentations in SARA that I've given about the electronics that's in that system, and it's been upgraded over the years. But I plan to talk mostly about observations in this talk. So, if you have questions about the system, we can go into that. But I'm probably not going to talk too much about the system other than to say, it's a pretty conventional system that captures channels, stores them away. It has a signal to noise ratio threshold that stores to the files. So the way the system works is we get this distance separation, and because of the beam widths and also the Doppler shift, the differential Doppler shift between the sites, we can basically create an overlapping beam or set of beams that says, okay, if there's something here on one of the antennas, is it on the other antenna? And if so, how far off in frequency is it? So all of these are synchronized with GPS, frequency and time, and we have oven-controlled oscillators at the sites that all lock up the frequency synthesizer, the first LO. And if we go through the math on this, on the Doppler shifts, we come up with an idea that we can pretty much reject signals that are outside the beam, single beam, to about 720,000 miles. In other words, a source 720,000 miles out will be in all 3 beams on the same frequency at the same time as a pulse, and could be, we wouldn't be able to differentiate from anything closer. Now, if things are closer, they're going to triangulate or come in on side lobes and have various amplitude and frequency offset differences that should be discernible. Now, this is a very simple system at the start, and it is not immune to RFI. In other words, you could have side lobes in space that get into the antennas, and then they produce anomalous results. So what I want to do is make sure that I point out that I'm a huge fan of multiple hypotheses, and this project involves lots of hypotheses. The first one I'm working on is just noise. I'm trying to say, can I reject a noise hypothesis using a system like this? And then over time, we can get into, okay, what about the RFI models and other possible explanations for simultaneous pulses on distant telescopes in narrow bandwidths, and then calculate likelihoods based on models for those things. So we've been running the system since 2017. Now, some of these observations I'm going to talk about, I've talked about in another SARA meeting, so I'm going to go through those pretty quickly because they basically got us started in a particular pointing direction. And this presentation is going to be entirely in that one pointing direction towards the star Rigel, that we have seen some anomalous results that are good for follow-up. Now, we started in 2017, and when I would go to Green Bank on my trips there as a volunteer, I would set up the computer there. And then Steve Plock, KL7IZW of the Deep Space Exploration Society, would drive to Haswell, set up there. And through February of 2019, we ran 135 hours of simultaneous transit scans at minus 7.6 declination. Okay, so we try to go around the clock. At the beginning, there were a lot of gaps, and then as time went on, I kept the system running the entire time, and Steve kept the system running the entire time. And then we did another 45 hours in April 2019, and then in December of 2019, we did 3 telescopes, and accumulated, we added all up, a total of 290 hours of simultaneous observations. Each one of these lines is around 2 days, generally. There's various overlaps and things. Okay, so first I'm going to go through the observations up until February of 2019. So in all of those observations, after post-processing the separate files that had signals that were above a 12 dB threshold and were on the same frequency at the same time, in the same quarter second, because the interval of the FFT is a quarter second. We saw these pulses around the circle here in right ascension, and right away I kind of noticed something interesting, that on consecutive days in August, which it turns out August was the first time we actually went through that particular right ascension, there were simultaneous pulses, and one of them was different by 1 hertz between Green Bank and Haswell, and the other one was off by 0.2 hertz from Green Bank to Haswell. That's after I do the various metrology, and we work through the overlap of the beams, and we calibrate the beams using a using NRAO 5690 as a calibration source. So it's roughly that direction at minus 7.6 declination is pointing towards the general direction of Rigel, and there's a few other stars in that area. So this has been a starting point to say, okay, let's continue running this, and let's keep looking in that direction. But also, we want to look at the other right ascensions as well, because they give us information about potential RFI and a potential noise hypothesis. And so what would we want to look for if we were to say, okay, what should we try to say is important to try to search for? And it turns out if you want to make a communication signal, you have to somehow make it different than noise. Now, the system for each one of the records that occurs, it stores all of the signal to noise ratio events that occur above the 12 dB threshold over time for each one of the bins. And it stores it independently for each one of the sites. And there aren't very many of these per quarter second. There's only about 10 to 20 of these events. So the idea is that if there was a communication signal present in this event, that this would have to look different than noise. Well, this ends up being a Poisson process, an exponential spacing between pulses when there is only noise present. So I kind of started off by saying, okay, let's just look for things that are close together. Well, they're close together between Haswell and Greenbank, but then maybe there's also close together tones in the Haswell data by itself and close together tones in the Greenbank data. And maybe each of those has signal to noise ratios that also show some significance. Now, of course, RFI can look like this as well, but this turned out to be the first sort of easiest way to see if there's anything interesting. So this is what happened on one of those two simultaneous pulses. So the Haswell Greenbank August pulses, that one of them was at -1 hertz. And if we look at all of the records that occurred in Greenbank within plus or minus 20 seconds of that event, they're plotted in this plot here, where 0 seconds at the middle is the time of the simultaneous pulse. So at this time, there was a simultaneous pulse that was 1 hertz off between Haswell and Greenbank. And it turned out in the Greenbank data that near that time, there were quite a large number of unusual close space tones in the Greenbank data. So something seemed to occur correlated with that. Now, these pulses up above, these points up above, represent really the noise pulses, the pulses that exceed the threshold that are due to noise. And we can calculate the statistics of those and say, yeah, if there are tones that are only 607 hertz apart, and they ought to be a few megahertz apart, then that's an extremely unlikely event. So we can go through the probabilities on these things, and we come up with some very, very low numbers, indicating that there was something unusual in the Greenbank data within plus or minus 10 seconds, or 20 seconds in this case, of the simultaneous pulse. Okay, April comes around, and I couldn't find anything really close in the data for all of our April run. I did find a case where they were off by 5.8 hertz. Now, it turns out there's a very slight change in Doppler across the beam, and there's also some metrology issues that can cause a little bit of an offset. And there's also the issue that maybe communication signals are not on exactly the same frequency, or maybe if it's RFI, it's not going to be on the same frequency exactly. It's still worthwhile looking at to see what might be there, given that there might be something in the system that are happening. So in this particular simultaneous pulse from April that was at 5.8 hertz off, I looked at the spectra of Haswell and the spectra of Greenbank. And this is what we saw. The red lines indicate areas where there are very close tones. So you can see 2 tones here, 2 tones here. The upper plot is the Greenbank spectrum. Now these are spectra that were in the quarter second that the simultaneous pulse occurred. And you can see over here on the left that the simultaneous pulse occurred 5.8 hertz off is the low pulse here, and one of these two. Well, it turned out that this one up in Greenbank had another tone next to it, very closely spaced. This one also had a high SNR on Haswell that was very closely spaced, and then there was another set closely spaced over here. So there was something there. There was also something up here, and all through this whole, the spectrum is sort of full of these highly anomalous events. In fact, there's a pair up here that are 1.9 kilohertz and 3.8 kilohertz off from a pair in Haswell. And The separation between these two is quite large. It's about 100 kilohertz. It's still a rare event in noise, but it's creating a very rare event, an even more rare event in noise at Haswell. So, you know, and another example is we could zoom in on the Haswell. Turns out this particular tone here is actually two tones that are spaced 1.66 kilohertz apart, which I had to zoom way out, and it still looks like almost one line. So this is the kind of thing that gets my attention and says, okay, something is unusual here, and noise doesn't seem to be working real well as an explanation. So then we did December 2019, running all the telescopes together. And this is a plot of the difference in frequency for simultaneous pulses that were measured in 2 and 3 telescope simultaneous observations. So I summed together all of the observations for all of the pairs. Now, there was nothing that showed up on all 3 telescopes at the same time and close to the same frequency. But between pairs of telescopes, there were, you know, quite a few that were within, in this case, I plotted at plus or minus 12 hertz. Now, if we take this area here from 4 to 6 hours right ascension, and we zoom in on it, we see down here that at 5.1 to 5.2, which this the target direction is 5.1 to 5.4. It depends on the antenna. It's a little bit less for the 60-foot, obviously, but there's also pointing uncertainty. So there was a collection of pulses at negative delta F between the antennas that sort of got my attention there. Now, of course, there are others over here, you know, so the statistical significance is maybe, you know, is questionable. But it turned out that when I looked at these, I found out that they had a very close right ascension. So the idea is if everything was just right on both, on all 3 antennas, and everything was peaked up for signal to noise ratio, then we might expect that they would all respond with SNR events, threshold crossings, that are aligned with a particular right ascension. That's just a guess. It's just a wild guess. So I went and binned the right ascensions, and I came up with a big spike right in that area where there are 5 right ascension differences observed. Now, this is the difference between right ascensions. So in other words, how close is this right ascension of this pair between 2 sites to another one? And it turns out there's a big spike right here, which says, all right, what's happening in other right ascensions? Well, it doesn't seem to have that close a correlation to a particular right ascension. So there does seem to be something there. And, you know, of course, this is a one way to look at it, you know, look at the data and say, all right, what is the binomial of this? And it turns out to be a pretty rare event, which we would expect, because we look at that and we say, well, if there are that many right ascensions in that bin, right ascension bin, well then, yeah, it's way higher than the mean. So now I came home from Green Bank, and the idea was, I've got this dish on the farm, which, could I use one telescope? Is that practical at all? And so I thought, well, all right, let's see now. What could I do? Well, I've got 2 orthogonal circular polarized signals, and I've got 2 receivers that run simultaneously. And as it turned out, it only has 1/3 duty cycle. So I bought 4 more computers and 4 more digitizers. So I now have 6 computers and 12 digitizers, 12 channels of digitizing that are gigasample. I run them at 62.5 megasamples per second, and then I run them into a Linux C code that I've written. So I expanded the system to run 100% duty cycle on the telescope for the 2 orthogonal circularly polarized pulses, thinking, okay, there were a bunch of close tones in the April 2nd data that were close together. So maybe there's something strange happening where 2 orthogonal circularly polarized pulses might be close together. So this is a bunch of observations that I did after I returned. And the paper that has been submitted for the proceedings does not include the July data. So it goes up through the June 2nd to 5th data. So a few of the slides, if you're following along there, a few of the slides in this presentation will be after the June 2nd to June 5th slides that are in the paper. So this is what I'm looking for, is I say, all right, I'm gonna have a left-hand circularly polarized pulse at some time on some RF frequency, and then I'm gonna have a right-hand circular polarized pulse on another frequency at a different time. What's the difference in time? What's the difference in frequency? Those two are Poisson exponential processes that can say, all right, we can make this a pretty rare event. So if someone is trying to get attention, they might want to do this. They might want to transmit this. The other thing is, and this is very speculative, but if we look at RFI models and we can think about the models, we could say, yeah, does RFI do this? Well, normally RFI fills out the Poisson sphere. It usually has lots of high SNR events, so they're going to respond on both polarizations. So this is kind of a feed for RFI models that might be used to calculate probability. And I have not started that other than just, guesswork. So this is what happened in the February to March data for the two polarizations. And this was when I was running it at the 1/3 duty cycle with only 2 computers. And it turned out that in the 5.1 to 5.4 region on the 26-foot dish, there was a sort of an anomalous set of pulses close to 0 hertz. Now, these are not simultaneous pulses. These are pulses that were greater than 0.3 seconds in time between them with 20 transits. And I don't have the number for the maximum that I used on this. I'd have to look that up. So this is 20 transits that occurred from February 20th to March 11th. And the size of the dot is the signal to noise ratio. So you'd say, well, all right, yeah, it's happening in other places. And of course, RFI could look like something that happens with low delta F. So this is, this is interesting, but, it could be other things too. So then what I did was I rigged it up so that I could track the pointing direction, which I call this Hipparchus 24472, because that happens to be a star that's it's the closest star, it's a red dwarf that is in the pointing direction of the 5.1 to 5.4 region that we're interested in. And so what I did was I tracked for various amounts of time, close to like 93 minutes on June 2nd, where I tracked the 26-foot dish across the pointing direction in Asnell. And I did it on June 2nd, June 3rd, June 4th, and June 5th. And this is what happened with pulses that were within plus or minus 4 seconds. This plot says 5, but the limit is actually 4. Within plus or minus 4 seconds, and within plus or minus 40 hertz of delta F, I saw this on June 2nd for simultaneous pulses. I'm sorry, I shouldn't call them simultaneous. They weren't exactly simultaneous, but sometimes I call these associated pulses. But it turned out there was a collection down here in this quadrant that seems statistically significant. And then on June 4th, there was a collection of pulses in this quadrant that seems significant. Not on June, but on June 3rd, it just looks like noise. And this is what I would expect. Now, these are the highest, this is the highest 8 signal noise ratios that occurred during the tracking. So while I was tracking this pointing direction, this is the highest 8 SNRs. This is the highest 9 SNRs. This is the highest 33 SNRs. And you can go through these numbers and say, well, yeah, even the highest ones like 1, 2, 3, 4, 5, et cetera, they look like they're uniformly distributed across quadrants, which is what we'd expect in noise. So there doesn't seem to be anything really here. And then on June 5th, there were pulses back again to one of the quadrants. Now we can do some calculations on this and calculate likelihood. For example, This particular set of SNRs has a noise model likelihood of 4 in 10,000 tries. So, of course, based on a, fair number of assumptions, as far as picking the endpoints, for example, I only picked the 9 SNRs. If I picked 12, I would have come up with a different number, etc. Okay, so what happened on July 7th to 10th? So basically what I did was I decided to not track for my next set of observations. And I ran it just for 4 days, allowing it to go through the beam without tracking, so transit only. And I said, all right, is there anything July 7th to 10th? And now I'm gonna get into what is called Bayesian data analysis. So what I'm trying to do is take a model and say, all right, we know a little bit about that model and we know what its likelihood is. And we have data that we know can fit that model, but we got to make sure that we can explain that we can tell ourselves what is the noise model likelihood that it explains the data, as opposed to the data given the noise model. And this is using Bayesian data analysis that's based on Bayes' law of probability that allows one to update a model's likelihood of explaining data, given that we have information about the model, noise model is valid, new data that we take, and there's also a factor which is necessary, which is that the data itself is valid. For example, if the data isn't valid, well then it's got a low likelihood and this whole thing explodes, and then everything looks like it could explain the results. So this had 2 quadrants on the with 3 outliers here, with pulses that appeared to be in this quadrant at the highest 10 signal noise ratios. So I use this to say, and by the way, if there's anyone listening who is a statistician and knowledgeable about Bayesian data analysis, please let's communicate, because I want to learn more about this. So the idea is that I create a model and I say, all right, the highest 10 SNRs tells me there's a model that there's something happening between these 2 quadrants, quadrant 2 and 4. So now let me take the next highest 40 SNRs as new data that is based on that model and say, what's the likelihood that fits it, apply the Bayesian formula in Bayesian data analysis to update the original model. Well, the original model here has a noise model likelihood of 0.12. So we'd say, all right, that doesn't really tell us very much, because noise could do that, and we could have just stumbled across one where it happened. And then the idea is that after we look at this data, we have to multiply by 0.08 for this data, which is just the data given the noise model, and it reduces the probability that the noise model explains the data to 0.01. Now again, this is not a very, I would call it low value, because we could have just stumbled across it again, just by chance over these 4 days. So then I took the 4 days, July 11th to 14th, and a really strange thing happened with that data. Each one of these numbers, 1, 2, 3, 4, is now the day, not the SNR level. This is the day, 1, 2, 3, and 4. And a weird thing happened. There was a huge concentration at minus 1.75 seconds for a whole bunch of pulses, which also says they were in this quadrant, not these 2 quadrants, not only in these 2 quadrants, but all at the same 1.75. Now, this has a very low likelihood by itself. So, that's one issue. But then what we can do is say, all right, let's apply the noise model and let's measure what happened for the 13th to the 40th ranked SNRs. So this is the highest 12 SNRs. These are all the SNRs below it. We're going to call that a new data set, and we're going to compare it to the model. And it turns out those SNRs were concentrated in another set of quadrants, quadrant 3 and quadrant 4. Still a very unlikely event. You can say, all right, there are 6 possibilities of other quadrants we could take, in pairs. So we got to multiply that by 6, and we come out with the numbers. And it turns out because of the way this is distributed, especially in this value, the noise model explains this quadrant concentrated data. It's extremely unlikely. And so because it's generally the case that hypotheses need to be refuted, they almost can never be totally proven. Refuting a hypothesis or a model is an approach. This is a very low number and says, yeah, noise doesn't quite explain this. Well, what about RFI? Could there be a RFI where a circularly polarized pulse shows up on one polarization and then the other one, separated by 1.75 seconds at these various differences in frequency over a period of 4 days, and while we were looking in the direction of Rigel? So that becomes the next thing to look at. So the first thing I looked at was, all right, what happens with all right, well, I didn't take all right ascensions, but I took right ascensions from 1.8 to 6 hours. And I said, all right, is there anything at 1.75 seconds? Maybe there's an RFI source that outputs opposite polarizations at exactly that time. And we look across there, and there isn't anything really significant. There are no lines that are jumping out and at the 1.75 second point. So this doesn't quite fit that it would be noise that would occur at some other time explaining this. And then this is just another view of the of that quadrant data that I showed earlier, which shows that at the highest SNRs, there was this concentration down here. And then when we look at the 1.8 to 6 hours, we say, well, we don't see any concentrations like high-low that are kind of spotty at other SNRs over the 1.8 to 6 hour period. So now it'd be possible to go back through this whole thing and check every 0.3 hours of right ascension, and that would be a good follow-up, additional thing. But getting into the idea that that's an RFI model, so not a noise model. The way this is looked at is we say, no, it's noise. Everything we're looking at other than maybe an interesting pointing direction is noise. So I'm going to leave this one up for a couple of seconds because this is the July 15th to 18th, 2020 near Rigel anomaly, pointing anomaly that's similar to the other ones. I took the lines off the graph, make it look, and each one of these numbers, 7, 8, 5, 6, 7, and 8 are the day associated with July 15th to 18th. And it turns out I found an anomaly in it. Does anybody see something that looks anomalous in this data? I'll give you a hint. Just start with -4 seconds and then just work your way across and say, is anything happening at a particular time on all of the days, and maybe with some kind of frequency concentration? Okay, well, I'm going to move along. I'm sure by now some of you have seen something kind of very unusual. And there's an unusual concentration, and it turns out to be at 0 seconds. Okay, now 0 seconds is one of those things that I get a little nervous about because 0 seconds of offset between two polarized right hand, left hand is linear potentially. So linear RFI could easily have caused this. But there is an anomaly in here that has a noise likelihood event of 6 in 10,000 tries. So there is there's a need to find out what is causing this because noise does not seem to fit. Now, before I go on, I just want to mention that I do have an RFI algorithm that rejects simultaneous durations on a particular frequency. Okay, it's basically a dwell algorithm, and it says if something dwells on one frequency, then reject that 1 kilohertz band. So it automatically goes through in the post-processing, and it rejects anything that lasts for more than a particular amount of time, and those are all parameters that I put into the RFI filter. They basically say, no, I'm looking for things that are on different times and different frequencies, not concentrated at one time or one frequency. So So then July 19th to 22nd comes along, and I go, well, all right, okay. Are high SNR anomalies happening every day? So it turns out in the 4 days of this data, there were high SNRs on this day, the last day, and the day before there were very few high SNRs. Again, deviating from what we would think is a really exponential type of distribution for Gaussian noise. So this has an interesting sort of thing, and again, this has a very low likelihood. And then if we go look at all the other, right, not all the other, but over 2.3 to 6.5 hours, we find, oh, look, well, there's another one right there. There's a gap between these 2 days where this occurred and this didn't, but it's at a different level of SNR. This is highest SNR, lowest SNR. It's at a different level. It's a little bit narrower gap than the other one is. And of course, it's also, I could have picked any of these all along the way. So the likelihood is, I have to multiply by maybe 6 or so, or 8 in order to compensate for it. I could have picked any of these to try to find that particular one. So this is all interesting and sort of saying what's going on. So the idea is that the noise model doesn't appear to explain the data very well. Now, I could be making a mistake on my noise model, and there could be other things going on. So these anomalies compel further observations. And I got to the point where I've said, well, I can't do much more with only one telescope here on the farm. So I'm building another one, and then I'm building a third one after that, but that's in the plans. So I'm building a 28-foot diameter under construction. And what I want to do is put it about 100 feet to the east from the dish that I currently have and say, okay, if it's there on the 26-foot dish, it better be on the 28-foot dish. Now, it also turns out that my 26-foot dish doesn't have surface accuracy that's all that great. So it has a low efficiency due to that. It's about 0.4 just due to surface accuracy issues. And so what I want to do is make this one have better surface accuracy, which means it should have a lower splatter type side lobe in offset from the main beam, and also pick up sensitivity, about 4 dB of additional sensitivity over the 26-foot. So with this antenna running at the same time, I should be able to see, well, if it's really there on that antenna, on the 26-foot dish, it better be on the 28-foot dish as well, if it's in the beam. And then the other thing I can do is depending on the signal to noise ratio of the pulses, I can say, all right, can I measure the phase difference? Now, it turns out these are broadband signals that are popping up in this data. So it's possible that if you get a flurry of pulses that are occurring, you can measure the phase difference without the ambiguity due to the aliasing that normally occurs when you only have 2 antennas in a direction finder. So I'd also like to have 3 synchronized telescopes. We also are planning in a couple of weeks, we'll be doing another Haswell, New Hampshire simultaneous operation. And then there's also a plan to start observing with the Ohio State University's Project Argus telescope. So they're working on a plan to simultaneously point that telescope. You may be familiar with that. It's an all-sky phased array that uses various algorithms to search the whole sky for pulses, and also can do beam forming, multiple beams simultaneously. And the idea is to work on the RFI models, get satellite experts, ideas, and encourage others to try these things. They're not too difficult to do, and given that my 26-foot dish is actually not a, it's got about a 4 dB down surface accuracy issue. A smaller antenna is probably possible to see some of these same unusual events. So the idea is to try to keep looking at this. So this is a picture of the 28-foot dish under construction here. It's gonna be pedal based as opposed to the other one, which I just climbed all over up in the air, putting mesh on it. And this has one of the rectangular petals along with the 7 of the 8 circular petals on the 12-foot central section. So there's going to be sections here and then triangular sections that I have to add the whole thing. And I did want to point out that on my farm, the animals, I basically rent this place from nature. You know, there's a porcupine over here. It's not in the picture right now, but this is its dinner area. When I set up to do optical telescope things at night, I'm using a chair that's pretty much in that spot right there. There's a hornet nest in the telescope base. This is a trailer that's going to be the telescope base for the 28-foot dish. I use the trailer as a rotating base for azimuth control. And this in the background here is another trailer that I'm going to use for another telescope. There's a giant hornet's nest in this thing, so I'm going to have to wait until it's very cold before I can get anywhere near any work that I need to do. I need to install the elevation axle on some scaffolding that I've attached to the side of this. There's a robin nest next to the front door right here, which it turns out now has a chick as of a couple of days ago, but I'm not going to go anywhere near that. In fact, when I saw the robin sitting in it, I decided about a month ago to not even use my front door. And so I haven't gone out my front door. I have to go around. It's a little bit of extra work, but not a big deal. And then a couple of days ago, both of the optical links, so I run fiber optic cable. I use RF over fiber from the dish that goes through this pipe here, this long pipe. Well, critters love to get inside of pipes and you know, make homes and such. And it turned out some kind of critter, probably a mouse, ate my fiber optic cables in the middle of the night out here about 3 days ago. So I had to go out there and fusion splice the fiber optic cables back on it, kind of the whole thing, finding it, etc., doing all that. So that's these are challenges, but this is an enormously fun project, and we'll see where the data takes the project. So I'd like to really thank Steve Plock, KL7IZW, who operates the Haswell system that's installed, and just all of the Deep Space Exploration Society team, Green Bank Observatory team, Ohio State University team, and family and friends. And thank you all for listening to this. Thank you very much.
Great, thanks, Skip. I got one question. Dish has a right hand and left hand circular question. That's a question. Could combine with various amplitude and phase to get any polarization. Should be possible to establish polarization of each event. Possible, useful.
Yes. Oh, sorry. Is that question goes on?
They're all questions.
I'll answer that one first. Yes, that's a great idea. One of the things I did was to say, in order to measure multiple polarizations, I need FFTs running on each one of those points on the Poincare sphere. Turns out it explodes pretty fast. If we want all the 4 places on the equator and right and left hand, we end up with 6 times a single channel. So what I decided to do was to say, all right, I got to start somewhere. So I'm going to start with right hand, left hand. Now, normally what happens is if somebody wants to do a polarization modulation or something like that, use polarization for a purpose, they might be likely going to choose right hand and left hand because it tends to not get disrupted by Faraday rotation in the atmosphere. So that's just a guess as to what that is, but certainly yes, that's a great idea. And with more processing, that would be a really important thing to do.
Okay. Ted Klein mentions that trailer frames to rotate dish is kind of like Jansky's antenna.
Yes. I actually built something like Jansky's antenna in college, but it didn't survive the winter. But yes, the idea is it does rotate on 2 wheels, but they're closer together. And then I have electric SUV, 4-wheeler winches. So basically winches you mount on the front of a 4-wheeler. I've got a bunch of them operating all over. There's a YouTube video on YouTube. If you just go to YouTube and type my name, you'll see the design of that antenna. I go through it.
Great. Anybody else have any other questions? That's all I got on chat right now. Okay, well, outstanding, Skip. This was very fun, and I've seen a couple of these things, and this is always I learned a ton of stuff every time you present this.